All right, so last lecture we talked about mass and volume and concentration and the unit conversions there between them, right? And the need for thermodynamics, because density is just not something we can look up on Google. It is dependent upon the state. So if you change the temperature or pressure, you change the internal energy, you change the entropy, you change the density. Right? And in fact, from a thermodynamic perspective, and this is something you haven't seen in your thermodynamics class yet necessarily, depending on how rigorous it was, the base units of thermodynamics are volume, internal energy, and entropy. Everything else in thermodynamics is what I like to call made up. Right? They are useful terms. So enthalpy, under what circumstances is enthalpy useful for? Yeah. Open systems, right? Because in an open system, you have a container and you have a pipe. Now, if I'm flowing material into this system, I'm flowing in with it certain fluids with certain chemical bonds with certain kinetic energies. That represents the internal energy of the system. But you're also pushing a little bit of volume at a certain pressure going into the system. So not only are you bringing with it the chemical bonds, internal energy, rotations, all that stuff, you're also giving it a little bit of extra work by pushing this fluid in, and then the system is pushing that fluid out. So that's the motivation behind enthalpy. Now, temperature and pressure, up until about the early 1900s or the late 1800s, we still used it. We still measured it, but we didn't actually know where it originated from. Does anyone know what happened in about 1890 that allows us to actually understand what temperature and pressure mean? Going back to your history of science. Yeah?
Does this have to do with Boltzmann, and he kind of figured out about entropy, and then didn't he die when he thought everyone made fun of him or something? Like they didn't like his ideas?
Very accurate. So Boltzmann and Maxwell developed the kinetic theory of gases somewhat independently. So the kinetic theory of gases was this radical idea that basically said everything is made up of really small things called atoms, right? And kinetic theory was initially neglected because in order to figure out and solve the work, you had to have very, 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 very small atoms to get everything to work out. So most physicists and scientists thought, hey, this is a neat mathematical trick. But in, I think, 1905, Einstein derived a theory of Brownian motion. Does anyone know what Brownian motion is? Brownian motion, what's Brownian motion? Yeah, so the little, like, small little particle you look at in a microscope, pollen was the one that people like to use. It jiggled around. And what Einstein found is that the jiggling rate and intensity was exactly the same distribution that would have been predicted by Boltzmann kinetic theory of gas. And then later, a French physicist, Jean Perrin, then further went on to measure Avogadro's number using Einstein and Boltzmann's work to demonstrate that, yes, atoms were causing Brownian motion and that they exist, and it validated Boltzmann's theory. Right? So now we know that temperature is the average kinetic energy of molecules. So how fast they're moving and what their mass is. Pressure is the continuous collisions of those together. Now, from a thermodynamic perspective, we have the first law of thermodynamics, which dictates how the internal energy should behave. We have the second law of thermodynamics, which talks about entropy. And then the V basically says that we have to exist in some universe with some dimensionality. So in our case, a 3D universe, right? So matter and volume can have energy and entropy. And this is how we derive everything with respect to thermodynamics. So pressure is actually understood to be coming from a relationship between these variables here, and that is the change in internal energy as you change the volume while holding the entropy constant, right? So it's the rate of change of how much the internal energy changes when you expand or contract the system, right? So it's how much does the system resist the changes in volume. Temperature is, let's see if I can get these units right, it is the change in internal energy with respect to changes in entropy while holding the volume constant. Because this is joules per Kelvin, so then you get the units right. That gives you units of Kelvin. right? So from a thermodynamic perspective, this is all early scientists and engineers had to work with before we understood the kinetic theory of gases. So this is probably not something you've seen in your thermodynamics class, but it's something you should see in your Thermo 2 next year in deriving all the other things. So for example, has anyone heard of the Gibbs free energy? What is the Gibbs free energy used for?
It's to determine whether a reaction is spontaneous or not, whether it happens.
Yeah, so that's one application of the Gibbs free energy. Another one is for phase equilibrium. At what pressure and temperature does a fluid transition from being a gas to a liquid, right? So the Gibbs free energy tells us how do two phases exist in equilibrium while the temperature and pressure are held constant. So these are all nice, convenient units. Has anyone heard of the Helmholtz energy? It's the same thing, but instead of holding temperature and pressure constant, you hold temperature and specific volume constant. So a lot of times if you're doing polymer physics or polymer phase behavior, you don't want to concern yourselves with pressure because, as it turns out, pressure is kind of a complicated thing. It's easier to keep it in the base units, and so you just work with that. Right, so when we're looking at pressure, if we have a gas, we have a very small number of particles colliding, well, very small relatively compared to a liquid, right? But these collisions happen, millions of times a second, right? Lots of little teeny collisions. Atoms are very small, but there's lots of atoms. So this net result, right, is a force of the fluid pushing out. Now, in the case of a liquid, we have a lot more of these collisions because the liquid density is substantially higher. And a good rule of thumb is that liquids are 1,000 times more dense than gases. That's a general rule, right? The difference here is that you've got a lot more collisions. Now, these are at the same temperature. So the temperature of the gas is equal to the temperature of the liquid. Temperature represents what again? Right, the velocity, the kinetic energy. Right, it tells us how fast these are moving. So this table, the molecules in this table are actually moving exactly as fast as the molecules in the air. Right, the molecules in a glass of water are moving exactly the same velocity as the molecules in the gas phase. Right, so why, if these two are in equilibrium with one another, meaning they have the same temperature and pressure, how can this one have so few collisions and result in the same force on the container wall, and this one can have so few collisions but still result, so many more collisions but still result in the same force? What's the difference between a gas and a liquid in terms of how they behave?
So really quick, this is obviously theoretical because this isn't actual case, but like in this case, those three on the liquid have an equal force as the one on the gas.
Correct.
Liquids are approximately compressible and gases are very compressible.
Not quite.
What was the question? Are we assuming these are the same substance?
Same substance. So they have the same mass of every atom. They have the same temperature, which means they have the same kinetic energy on average. Okay, I don't know who's in the back up here.
In a liquid, you're more likely to have intermolecular forces. Like with water, you'd have hydrogen bonding in liquid water, whereas in vapor water, you wouldn't.
Exactly. So they're moving just as fast, but there's a net pull of all the fluid over here pulls them in this way. Right? So when they hit the wall, they hit it with less force because they're traveling. Their average energy is the same, right? But because as soon as this molecule leaves all of its friends and gets near the interface, right, there's a net pull going back this way, right? And that's the cohesive energy. So what's another phenomenon that you've all seen in your life that manifests in this same behavior, right? Where fluid molecules are attracted to one another and it manifests in something interesting. Surface tension. Right? Surface tension is the result of there being an absence of particles on the other side of an interface. Because if I had particles on this side, they would be pulling the molecules this way, and then you would have no net pressure on that interface. So when you have the interface, the lack of friends of the molecules, right, allows them to sort of suck and pull in. And so then if I were to deform this surface here, I create more interface, right? That means that there's more molecules that don't have friends, and so the fluid resists that. And that's why you get surface tension and you have those effects. Make sense? All right. So temperature and pressure, we love them. They're great. They're super easy to measure. Thermodynamically, they are derived variables that are very convenient. We didn't know what their meaning was until we understood atomic theory that was enabled by Boltzmann. Back in the olden days of thermodynamics, they didn't know what temperature and pressure meant, right? There was an old theory called caloric theory that described how temperature behaved. Caloric was a weightless, massless, invisible fluid that contained heat. And so they thought that when heat traveled from high temperatures to low temperatures, that it was this fluid caloric flowing from high temperatures to low temperatures. So the reason why I bring this up is because I think, how many people love thermodynamics? All right, maybe 5, 10%?
It's a love-hate relationship.
Okay. Who finds the thermodynamic variables to be intuitive? Okay, a few people. Like, you can close your eyes and you can imagine what a bucket of entropy looks like. Right? If someone tells me I have a barrel of oil, I can be like, oh yeah, a barrel of oil. Yeah, I get that. It's that volume. If someone says 100 kilograms, I can be like, yeah, that's heavy, right? But if someone says 100 kilojoules per mole of internal energy, is that something we can just intuitively visualize? So what we have to remember about thermodynamics and thermodynamic variables is that they were derived before we knew of the existence of atoms. Okay? So when we deal with internal energy, as we will in a couple of weeks in this class, when we deal with enthalpy in a couple of weeks in this class, we may get frustrated that it's really non-intuitive. But that is the system that was developed that works really well. Right? So you just kind of have to grin and bear it and realize that the reason why we have these abstract terms like internal energy, right? What are the sources of internal energy? How do fluids get their energy? Volunteers.
Chemical bonds.
Chemical bonds is one. What else?
Gravitational. Actually, no, I guess
That is a form of potential energy, but not something we would consider necessarily in a chemical engineering class, right? The example that I always like to give for gravitational potential energy and kinetic energy is I have my morning coffee, right? And let's say it's gone tepid. And I say, all right, I'll give one of you $10.
I'll do it.
And I want you to reheat my coffee, and you got 2 ways of doing it. So let's say 3 ways of doing it, okay? You can take it and you can throw it against the wall, right? Transfer kinetic energy into this coffee and smash it into the wall. Or you can go on the top of the Warnock building and you can drop it off a bunch of times. Or you can put it on a little gas stove and heat it up, right? Which one would we choose?
Third option.
Third option. Kinetic energy and potential energy are fun little toy problems for chemical engineers, but in the grand scheme of things, they are insignificant. Now, if we were designing a hydroelectric power plant, absolutely we got to worry about gravitational potential energy. But as chemical engineers, the energy stored in chemical bonds is massively more significant than anything that comes close in gravitational and kinetic energy. So we generally neglect that. But if you take a mechanical engineering or civil engineering thermodynamics class, they will be very concerned with those because the forces and energies that they work with, those are relevant contributions. For chemical engineers, we don't care. Okay, so we got chemical bonds. What are the other ways that molecules store energy?
Kinetically through that like Brownian motion that you're talking about?
Right, so the velocity of the molecules, they have kinetic energy. What else?
Ionization.
Ionization is one. Yes, that would be like an electronic energy state. Do you have extra electrons? Do you have fewer electrons? Do you have excited electrons? What else?
I mean, we kind of already said the kinetic energy of the molecules, but maybe the temperature?
So the temperature is the kinetic energy, so that represents the kinetic energy. And so what happens then is when temperature goes from high to low, right, is you've got a fast particle that hits another particle and it imparts some of that energy, right? So that's how that transfers, yes. Polarity, maybe for complex liquids, right? If you have a strong cohesive energy, if you have polarity, the molecules like each other. Yeah?
You can store energy with pressure.
Yes, you can. So that would be the PV component of the internal, of the enthalpy. Yes?
Nuclearly.
You actually can store energy in nuclear states, right? The nucleus is a quantum mechanical particle, right? So you can have excited nuclear quantum states, but that's something that's far outside of that class. Yes, last one here.
What about like excited electrons?
So excited electrons is one definitely, and that's why fire glows, right? Ionization. Yes, we got electrons twice. Chemical bond vibrations, right? Atoms jiggling like this, right? Like they have little mini springs that stores energy, and also molecular rotations, right? So if you have an oxygen molecule, it can rotate. That stores energy. That's why the heat capacity of something like argon, which is a noble gas, is lower than the heat capacity of oxygen. Oxygen has these bond vibrations. It also has rotations that store energy. Okay? So that is my introduction to temperature and pressure. So we're going to go over a couple of things that we're going to be applying with respect to temperature and pressure concepts. The first one, okay, so one of the simplest ways that we can measure the pressure is by converting it. Yeah, question?
Yeah, this is just on the last thing, the gas and liquid thing. So in your example, the liquid has the same pressure as the gas. And is that just demonstrating that they can have the same pressure, or do liquids always have the same pressure?
If they are in phase equilibrium, they have to have the same pressure. So if these two, let's say this is a saturated vapor and this is a saturated liquid, that would mean that the Gibbs free energy of the liquid is equal to the Gibbs free energy of the vapor, and that they have to be at the same temperature of the liquid is equal to the temperature of the vapor. The pressure of the liquid equals the pressure of the vapor, and the Gibbs free energy is the enthalpy minus the temperature times the entropy, right? So the Gibbs free energies have to be constant, and the temperatures and pressures have to be constant. And so,
Phase equilibrium is like existing gas and liquid the same.
yeah, so like for example, water at atmospheric pressure at 100 degrees Celsius is a saturated liquid or a saturated vapor. They're at the same temperature, the same pressure. If that's the case, then the reason why they have the same pressure is because this gas molecule has no friends pulling it back in, right? And so it slams into the wall with its full kinetic energy force, whereas with the liquid, it has friends pulling it back in, sort of like holding it back in a barroom brawl, right? And so it doesn't hit the wall with quite so much force, even though they're traveling at the same velocity, right? So it'll leave, but then it'll feel the pull of all of its friends coming back, right? So it has to leave that thing. This is what you'll talk about in thermo 2, right? So thermo 1, you don't have to worry about Gibbs free energy. All right, so for pressure, oftentimes we can measure pressure in terms of a unit called hydrostatic head, right? And that is the effective height of a column of fluid or column of rock. It wouldn't be hydrostatic then, right? This column exerts a force on the bottom, right? So if you go swim deep in the pool, you can feel the pressure on your ears. This is the hydrostatic head. So at the top of the column, we have P naught, and this is the pressure pushing down on the column. So this could be the atmospheric pressure. So if you're in a pool, right, this would be the pressure of the atmosphere pushing on the pool. And then as you add more and more water, the weight of the water squeezes down also. Now at the bottom of a column of height h, we're going to have some pressure at the bottom. The pressure at the bottom is the density, the gravitational acceleration, plus the initial pressure. So we're squeezing pressure here, and that this term accounts for how much force is being exerted on the bottom. Now, it doesn't matter how wide the column is, right? Because pressure is force per unit area, so the area cancels out. It doesn't matter how wide the column is, it only matters how tall the column is. So let's go through and double check that we understand what's going on by looking at the units. So what are the units of pressure in SI? What do we like to use?
Kilograms per meters cubed.
Pascals.
Pascals, which is someone said it, I think, Newton per meter squared. Right? What's a Newton? Kilogram meter per second squared. How did we come up with the Newton is that?
I just memorized
Mass
it.
times acceleration.
Mass times acceleration is a good one, right? Mass times acceleration divided by meters squared. So that gives us the base units of a Pascal as kilograms per meter second squared. Well, that doesn't mean a whole lot to me, but that's what it is, right? Now let's double check that the units on the right-hand side give us these same base units. Okay, so let's look at the rho GH. Rho GH, SI units of density, kilograms per meter cubed. Gravitational acceleration, meters per second squared. And for height, meters. Okay, so we get the same thing, right? Kilograms, we got 2 meters on top, they cancel out, so we get kilograms per meter second squared. Thank goodness it works out. Now, do I sometimes forget this equation? Absolutely. But I know I can suss it out just by looking at the units, right? So I can re-remember what's going on based on the units. Okay, so the manometer is what we'll talk about in a moment, is a measurement device that measures the pressure using the density of a fluid. Now, the more common ones that we look at are called Bourdon gauges. Right, where we have, this is like how you measure your tire pressure, right? And you've got some sort of a needle that points out. So how this one works is it's got some sort of a curved metal. As a force pushes on here, it bends this metal, and then a series of gears and things cause this pressure to go up, right? So you convert this pressure force to a mechanical distortion, and then that measures it there. So you just have to calibrate the thickness and the dimensions of that little coiled spring, and then you can measure the pressure, right? So this is one way we can do it. Now, the manometer is the thing that you'd want to use if you go to Gilligan's Island, for example. Oh, one last thing before I do the manometer. I forgot. Okay, so when we refer to pressure, there's typically 3 ways that we're going to report it. One is PATM. This is the atmospheric pressure. This is the hydrostatic pressure of air, right? Air has a much lower density, so that means you have to have a lot of air in order for the weight of the air to exert an appreciable pressure. So for the case of water, 1 atmosphere is approximately 10 meters or 30 feet, right? So every 30 feet that you go down in water, you experience 1 additional atmospheric pressure. So in the case of Salt Lake City, do we have atmospheric pressure that's the same as at sea level?
No.
No, because we have less air on top of us because we are higher up in the mountains. Now, this calculation for atmospheric pressure is not as trivial as water because the air is not at the same temperature, it's not at the same pressure. So as you go up in altitude, your temperature changes, your density changes, so you have to have a little bit more complicated of a calculation. We also have P absolute. Right, so this is the pressure of the system relative to a vacuum. So if I had a fluid in a box, and this is a vacuum here, right, that would be the absolute pressure, how much it's pushing against a vacuum. Because normally, if this is not a vacuum, this fluid is also pushing back against the system, and then you have an imbalance of these pressures. Okay? And the last one is gauge. And this is relative to atmosphere. So your tire pressure is like what? 40, 50 psi? That's relative to the surrounding air that's also pushing on the outside of your tires. Right? So that's the relative pressure. So any thermodynamic calculation, like the ideal gas law, which of these pressures do you use? Always use absolute, right? But for a lot of conveniences, atmospheric and gauge pressures are necessary. Okay, so the manometer is a pressure measurement device that can tell us what the differential pressure is between two fluids, or two streams. Okay, so we've got some U-bend, and this is connected to something up there. Could be connected, could be not. So we're going to have pressure 1 pushing down on the left column. We're going to have pressure 2 pushing down on the right column. We're going to have some height on the left-hand side called D1. We're going to have some height pushing on the right-hand side called D2. And then we're going to have some height here, H, that is the difference. Now, the reason for this notation is we don't necessarily know if fluids 1, 2, and the working fluid here, right, which has a density of rho F, rho 1, and rho 2. We don't necessarily know that these are all the same fluids, so this is a general equation that we're going to derive. Now, which of these two sides, 1 or 2, has the higher pressure? 1, right? Because it's pushing down at a force equal, right, to how much this one is going up. So at the bottom here, these pressures are equivalent. Because if it wasn't, it would just continue to rise, right? So if the pressures are imbalanced, you'll have movement. If there's no movement, then you're in an equilibrium state. So that means at some point your pressures have to be equal. So at the bottom here, the pressures are equal. And because going from the bottom to this height here, right, it's the same amount of fluid height on either side, then we know the pressures at that point are equal. Does that make sense?
Is that a rho or a p?
These two are pressures, these two are rhos, this one's a rho. Okay, so the general manometer equation is we're just going to make the pressures at the bottom of these columns equal by considering the hydrostatic pressure head using that guy up there. So on the left-hand side, we have pressure 1 pushing down on the left-hand side, and then we have the hydrostatic head of fluid 1. So that's going to be plus the density of fluid 1, the gravitational acceleration, and the height D1. This is going to be equal to the right-hand side, which is going to have pressure 2 plus density 2, gravitational acceleration, height 2 plus density of the working fluid of the system in the manometer. Yeah?
Sorry, while I was writing stuff down, I must have missed it. So can you go over the density stuff again? So we have 3 liquids in here, or 2, or?
3 liquids potentially. So this is the generalized equation that we can then simplify down.
Okay. And
So
the liquids are they anything specific, or?
no, it doesn't have to be. So in this case here, for example, this could be, so a manometer is really useful for air ducts, right? Because the pressure of air in an air duct is relatively small. So you may have water in your manometer tube, and you may connect it from one duct to another duct to measure the pressure loss going through a constriction or how much pressure is being gained by a fan. So then your working fluid here could be the same. It could be the air, and air is low density, so you may just neglect these two terms here.
Oh,
right?
so when we say fluid, it's not always like a liquid.
Doesn't have to be liquid, yeah. Or it could be 2 liquids. Like this could be an oil, right? And you could be measuring the difference between 2 tanks with water and salt water, for example. Yeah.
So rho F is just like a medium.
Yes, so rho F is like the working fluid of the manometer. It could be water. In the case of a mercury barometer, right, it's mercury. Now, we don't use those anymore because mercury is not super good on the body, to put it lightly. All right, so all we're doing here is just applying the hydrostatic pressure and then just adding all the contributions up. So we've got pressure 1, and then we've got the density and pressure of the fluid. Pressure 2, the pressure and density of fluid 1, the pressure and density of the working fluid, fluid F. And this is our general manometer equation. right? Because we know that at the bottom, these pressures are equal, right? So if fluid 1 and fluid 2 are the same, that is a differential manometer. Look at that, someone else is doing stuff. Huh? There are 3, I guess. 1, 2, 3, 4, 5, 6, yeah. So this is the hidden one. Oops, I just broke that chalk. All right, so the differential manometer. Right here, fluid 1 equals fluid 2, so density 1 equals density 2, and we're just going to simplify that expression. Now what this would look like in practice is if you've got a flowing system, right, and you want to measure how much pressure is being lost or gained going through some sort of a process, right, we just put a port here, we put a port here, we connect the manometer, and then we have some working fluid that is in that manometer. So in fluid mechanics, we can actually put an intentional constriction or an orifice in here, and based on the pressure loss, you can actually figure out what the volumetric or mass flow rate of the system is, right? So these can be designed intentionally to lose a little pressure because how much pressure is being lost is going to be relatable to the flow rate, right? The faster the fluid flows, the constriction will cause it to lose more pressure, right? So you can kind of think of, it makes intuitive sense, I guess. All right, so all we're going to do is simplify that manometer equation there with fluid 1 equals fluid 2, the densities there being equal. I'll just skip over the algebra here, but basically, let me just write this is D1, this is D2, but the densities are equal. This part here is H. So I'm going to skip over the algebra, but really all it is just set rho 1 equal to rho 2 and then simplify that expression. So that'll give us that pressure 1 minus pressure 2, right? This is the differential pressure that we're trying to measure, how much pressure is lost from point 1 to point 2, or how much is gained if it's a pressurization system, is equal to GH rho F minus rho, right? And rho is the density of the fluid that we're working with. So if this is an airstream, we can probably neglect this density, right? And so that just tells us, based on the height of the working fluid, let's say it's water in a water manometer, just the height that it gets pushed up tells you what the pressure difference is between those two streams. Make sense? Question?
That second row, or that first row after the GH, is that just the working fluid?
Sorry, that's bad, yep. Rho F, my bad. I got excited. Okay, so then we also have a couple of other manometers that I'm not going to derive the equations for. An open-ended manometer measures the pressure of a stream relative to the atmosphere. Right, so which is winning the battle, the fluid on the inside or the atmospheric pressure? Right, this is an open-ended manometer. And then we also have a closed manometer. In which you're measuring the pressure relative to a vacuum. So this is closed, and you may have some fluid level here. So a closed manometer is a mercury barometer. Why do we use mercury to measure atmospheric pressure? Has anyone ever seen a mercury barometer? We've basically eliminated them from our labs.
Isn't it just liquid, mercury in like a puddle of water, like up in a tube, upside down?
Yeah, so you basically have a tube with a closed end. You pour a bunch of mercury in there, kind of put your finger on it, and then dip it and put it into a pool of mercury. Yeah.
I haven't seen it, but I assume that mercury is the densest liquid at room temperature.
Right. So the reason is because 1 atmosphere is 30 feet of water. So if I wanted to make a water barometer, I would have to have a column that's 30 feet tall. So because the density of mercury is so much higher, it can be about yay big. Right? Okay. So that's my overview for pressure. Now temperature, not quite sure how much detail I should go into. I'm assuming a lot of you folks did temperature conversions already. So do we want to just shout out what are the main units of temperature that we're used to? Kelvin, Celsius, what else? Rankine and? All right, those are the main ones. What's the difference between Rankine and Fahrenheit?
A number of degrees.
Right, it's the reference. Right, what's the reference for Fahrenheit?
The freezing point of water.
Almost. Freezing point is salt water. And then what's the 100-degree reference for Fahrenheit? Yeah. I still like Fahrenheit. I think Fahrenheit's great. So yes, the reference for Fahrenheit is approximately 100 is body temperature, and 0 is like about the temperature that seawater may freeze, right? So a brine. So I think Fahrenheit is nice for like temperature and climate for people, but for scientific calculations, I don't think I've ever used Fahrenheit. Celsius, what's the reference for Celsius? Freezing point of water, boiling point of water, and Kelvin is absolute 0. So the key thing that we have to remember here is that when we're converting between temperatures, we have to differentiate between if we're converting between references or intervals. Right? So if I have a temperature increase of 10 degrees Fahrenheit, does it matter if I use Rankine or Fahrenheit? No, they have the same interval. If I'm doing a 10 degree C increase, comparing that to a 10 degree to a Fahrenheit increase, do I care that the references are different? No. 10 degree C increase, right, going from 20 to 30, how much does that correspond to a Fahrenheit increase? Right, I don't care what the starting point is. I'm just saying I'm increasing it by 10. Right, so I've got a little line here that I think is convenient. So for temperature in Celsius, we have 0, which is the freezing point of water. Now for temperature in Kelvin, and by convention we don't write degrees Kelvin, it's just Kelvin, right? What is 0 Celsius in Kelvin units? All right, so we got the 1.5. Let's be precise here, okay? And then we're going to go all the way out here, and then I chose a point that's convenient. So this is 5 degrees Celsius, which is 278 point blah, 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 Kelvin, right? So this is a delta T of 5 degrees Celsius, which is 5 Kelvin, right? The absolute reference is different, right? So if I wanted to tell you it was this temperature, I would have to specify the reference of the units. But the interval here is 5. So if I increase something by 5 degrees Celsius, that's the same as 5 degrees Kelvin. It's the same interval. Now for Fahrenheit, right, if I want to use the same number bar system versus Rankine, and I think Rankine is degrees Rankine, so just to make it super fun. What is 0 Celsius in Fahrenheit? 32. And for Rankine, I don't know this one. I have to look at my notes. Apparently, it is 492. There we go. Okay. So then I go all the way out here. So if I increase from 0 to 5 in Celsius, that is the equivalent of increasing to 41 degrees Fahrenheit or 501 degrees Rankine. So the delta T here is equal to 9 degrees Fahrenheit, which is the same as 9 degrees Rankine. So the interval between Celsius and Fahrenheit is 9/5 or 5/9.
Sorry, what's the reference for Rankine?
Absolute 0. So Rankine is the Kelvin equivalent for the American engineering units. Yes?
Is that that where the 9/5 comes when you convert?
Yep. So the interval is for every 9 Fahrenheit, you get 5 Celsius. But if I'm converting from Celsius to Kelvin, I'm shifting the reference. If I'm converting between, let's say, changing 5 degrees Celsius, that's the same as changing 5 degrees Kelvin. And that comes up in heat capacity, right? So in heat capacity, I can say it's 4.1 joules per kilogram Celsius or joules per kilogram Kelvin. That's exactly the same. Okay, so the last thing that I wanted to cover here is measurement. So the reason why we love temperature and pressure is because they're easy to measure. I slap a manometer on, or I put a Bourdon gauge or some other pressure transducer, and I can know the pressure. For temperature, I do the same thing, right? I can put a thermometer into the system here, right? How does a thermometer work? When the temperature goes up, the line goes up. Why does the line go up? Yeah.
Is it because the fluid inside of it starts generating more pressure against the other fluid in there?
Not quite. It's because, yeah? Thermal expansion. So the density goes down, so the volume of the fluid goes up. Right? So when you heat this up, you got a reservoir that expands a little bit, and then that moves the line. Now, who's used a thermocouple? Okay. How does a thermocouple work?
In some metal things, so you have a piece of metal,
Mm-hmm.
and that, when that's increasing the heat, you have a computer thermocouple that reads that.
Right. So a thermocouple is a voltage meter. If I take metals of 2 different types, so like a type J thermocouple versus the type K thermocouple, what that means is it tells you what's metal A and what's metal B. Right? So what happens is that the energy levels of the electrons in the 2 metals are at different points. So when I put them together, there's a voltage potential difference. The electrons from the higher energy metal want to cascade down to the low energy metal. A voltmeter measures what that is. So a thermocouple meter is just a fancy voltmeter that has internal calibrations. As it turns out, this energy level of the voltage is very well calibrated to temperature changes. So all they do is as the temperature increases, it changes the voltage difference between the thermocouple wires, and that's how we can very easily measure the temperature. But both of these are based on calibrations. How much does this fluid expand as the temperature increases? How much does the voltage change in a thermocouple? We love temperature and pressure because they're super easy to measure, but recall, they are made up variables in terms of thermodynamics. All right, no class on Monday. See you on Wednesday. I'm going to post the first homework, and have a good long weekend.